Yeah, welcome back, everybody. Before we go on, I wanted to just hear how the speed is. So you can indicate, like, is it too fast? Is it too slow? Is it just right? You can vote there. So add a little O, and this helps us. And you can already anticipate where this is going next and in the next hour. So the plan is we will then talk about what are the tools and strategies that we use to find out how many cores we should ask Slurm for. And again, we will discuss why does it matter? Why does it matter for you? Why does it matter for everybody else? We will show you a couple of tools that we use. And again, you will get 15 minutes to try this out. I will have an example for you that you can try, but also you can try it out with your own code. And I do encourage you to try this out with your own code, at least once. Again, it's part of the calibration. And then we will do another break, and then we will have half an hour at the end of Q&A. It can be about memory cores, but it can be about anything else, computing and programming related. So are there so many people listening, or do we need to put the link to the Zoom? 30 people are online. So it would be nice to hear how the speed is. Only 2 votes. But should we go on and have a look at choosing cores? And again, the material is linked, and maybe let me also put the link into the collaborative document so that you know where we are. We are now how to choose number of cores. We will roughly follow this documentation page that it will be this page, and I linked it here from our document. And I will again start with an example. And this is from testing. Let's remove. It's again an example I got from somebody. Scripts, they get inherited from generation of PhDs to generation of PhDs. So I inherited this. I'm expected to run this setup, and now I'm also expected to now we focus on this line here. We learned yesterday and today and in previous courses that we need to tell Slurm how many cores we want to use. And here I inherited something and it asked for 16. And is that a good number? I don't know. I think the first thing anybody will do, or the first thing I would do, is I just want to see whether this is working at all.
Radovan?
Mm-hmm.
I'm not sure if this is not too far out of, but like it doesn't say cores, it says tasks.
Mm-hmm.
And this is like confusing.
It
was confusing for me a long time what the difference is. Can we like quickly at least mention it?
I think that's a really good question. And there is a lot of, it is confusing. And one reason why it is confusing is that hardware has evolved a lot over the last 2-3 decades. And there is a lot of history in the names. So here I'm asking for 16 tasks. Why is it a task? Shouldn't it be cores? Maybe there is a way to ask for cores. Is that the same thing? So historically, the term tasks comes from MPI, message passing interface, that Ole mentioned. But it is, these days, it's more general than that. So by this, I'm asking for 16 cores, but it's not, I wish I could say 16 processors or CPUs, but that's not really true, because these days, again, historically, they used to be independent CPUs, little chips, 16 of them. But these days we have several cores on the same chip. I wonder whether this was any clearer now. There are other terms. So there's tasks, but so it comes from MPI, but it means cores. There is also threads, and threads and tasks is not the same thing.
What I like to think, what helps me at least, or what I think is set tasks to 1 in this case, and then cores per task to 16. It makes it a bit more clearer. I think for me at least.
All right, we can try that. I think the result will be the same, hopefully. So what would you do is you would do
task to 1 or
task to 1, and then
dispatch cores per task.
Task equals 16.
Yeah.
Okay, maybe that's clearer. Yes, because then let's try and let's see what we get. I'm asking for 10 minutes. This will take much less time than that. I think this example will take a couple of seconds. At this moment, only watch what we do. Later, you will get a chance to experiment a bit with this example yourself. I will submit and see what happens. Ooh.
Yeah. Maybe I got it wrong then. I'm trying to figure it out on the back, but
okay,
wasn't close enough.
So that is it. Maybe n cores, num cores. Should I go back to what I had?
Yeah, just go back to what you had.
Okay, let's try that. Submit it. While this is running, there is also memory, but we will here not focus on the memory. We here focus on tasks. In this particular case, the two are independent, but sometimes they depend on each other. So some programs, if you change one number, you also need to change the other number. So they can be decoupled or not. So then when I calibrate my computation for the first time ever, I might need to, turn two dials at the same time. Depends on what you do. In this case, we only focus on how many cores we get. 16. Am I still running? No, it finished. Hopefully it finished in a good way. Let's inspect the output. Any errors? So I asked for 10 minutes, but it only ran for 42 seconds. If all my jobs would finish in 42 seconds, it would be good not to ask for 10 minutes, because the Slurm job, again, it doesn't know that it will take only 42 seconds. So if I know that it will always be less than a minute, I should change my script and ask for 1 minute. But here we focus more about how many cores we used and how long it took. 42 seconds to get here. Where does this thing come from? This comes from I also put the time command in front of srun because I want to get extra information. This will also give me, it will give me timing, but only for this line. So it will not time anything that happened before. It will only time this particular line. And now the time command told me that this took, well, 42 seconds in total, but that one line took 39 seconds. But it finished, it didn't crash. I could now happily compute on 16 cores happily ever after. But let's discuss why should I worry about this number? Why should I calibrate it? What are the pros and cons? And the reasons are similar to the previous session. if here I'm running on Saga. On Saga we can be several people on the same node. So while I ask for 16, somebody else can use the 24 remaining cores. If I would run the same job on From is another cluster that we have. On From, we are always alone on a compute node. And if I only ask for 16 cores, then the remaining cores are idle. They have nothing to do, and nobody's using them, which is a shame. So asking for too few can be a problem, because then resources maybe are idling. But it can also be a problem asking for too many. One thing I see often when working in support is that somebody gets a script from a colleague, didn't write a script, doesn't know is it parallelized or not, is it MPI, OpenMP, all of these terms that we heard yesterday and today, doesn't know, it's just a Python script, it's an R script. And then they think that the bigger number I choose here, the sooner it will finish. And very often that's not true. There are calculations that cannot use more than one core. So even if I tell Slurm to please reserve 16 for me, then 15 of them will have nothing to do, but I will still pay for them with my quota. And they will be not usable for anybody else. Then there are calculations that are parallel, but Ole showed us these nice graphs that as we add more and more and more processes to it, it will not necessarily finish sooner. And here I can show you. Can we demonstrate it? I want to demonstrate it. What if I take, I don't know, 64? Sounds like a nice number. And I will submit it again. And let's see what we get this time. Still computing. I'm somehow expecting that it will take less time than the 16 processor run. Almost done. Still computing. 30 seconds in.
Do you also realize, did you notice, you asked for 64, but earlier we looked at that there's only in most nodes on Saga, it's only 40 cores, and some have 50 for 2 or something. So now we have asked for more cores or for more tasks than we have actually in one node.
Yeah.
So
here my calculation is now distributed over the C34 and C36. So if I wanted to again look at how is my job doing and I wanted to SSH into it, I could SSH into the C34 and into the C36, and I would see that however many are on one node and the remaining part is on the other node. And now they need to communicate from one node to the other. This may or may not be a problem. Am I still now? Now it's finished. And now I will grep real. Why am I doing that? Because the real is the output from the time command. And this is the job that I ran first. This is the job that I ran second. So when I quadrupled the number of cores, but the time didn't go down, it even went up. And at some point, the cores spent more time communicating than actually computing. I like to compare it with trying to write a manuscript with very, very, very many authors. then most of the time we'll go into scheduling meetings and communicating changes rather than the actual writing. So at some point, unless this is how did Ole call it? The calculations that are absolutely independent of each other and there is no communication. There is a term called embarrassingly parallel, but I don't like it. I don't like the term embarrassingly parallel. But completely independent. So unless they are completely independent, very often at some point communication will outweigh computation. And this kind of calibration is really important to do.
And also some software like Python or R scripts are usually not MPI parallelized. So even if they can, sometimes you can only actually use one core visually. Sometimes you use underlying libraries, which you might not know about, and then you can use multiple cores. But that you can use multiple nodes doesn't usually happen if you don't at least put some work into that. So often it's a good time to specify nodes equal 1 to not get in this problem that suddenly you have cores on multiple nodes which then can't talk to each other because they have to use the interconnect network.
And so again, we have discussed why does it matter, and the short answer is it matters because we don't want to waste CPUs. Not for you, and we don't want to waste CPUs for everybody else. And then we have a couple of tools again in our toolbox. We will do an exercise in a moment, and then later, if we have time, and I think we will have time, maybe we will manage to look at a Python example where we don't really know and this will be a Python example that actually can benefit from multiple cores, but it's really hard to see. And we will see how we can study this. There are different tools, but before I present them, how do you do it, Jan? Like if you are in the problem that I'm in, how do you calibrate this thing typically in your work?
I mean, I would probably start with if I know this is something which runs on one node, and assuming it's not I got from someone some script to run or some kind of workflow. I would probably ask for one node and then for the full node and then check this. I like Ceph a lot, but otherwise you can also go with top into the node and look after the job run, what is your average CPU utilization? How much of the CPU cores did you actually use of the power you have?
Yeah. So Ceph was mentioned. I can do Ceph job ID, and it will print some stuff. But here the interesting part is how much time was spent. As we add more and more cores, hopefully the time goes down. We should stop at the moment when it doesn't go down anymore. It will also tell me a bit about CPU efficiency. Where is the time spent? So that's a good starting point.
Like what you have here, for example, you see on the top you have use 4 cores and it took 13 seconds, and the bottom it was 8 cores and used 10 seconds. And now then you have to decide, is it worth your allocation? Is it something which might be 10 days with, I don't know, 8 cores, but it would be 16 days with 4 cores, and then the maximum time you can actually run is 14 days, then you might have to invest the money, otherwise basically the allocation and the CPUs. But sometimes it makes more sense to start 2 jobs in parallel with a lower core count and get because the difference is not double or half, so it doesn't scale very well. You have a bit of a reduction. So I would say probably in this case, if it makes sense, and you run 2 jobs parallel with each 4 cores to get more out of your quota.
There's also job stats. I want to just query what job stat tells me. Yeah. It also tells me a bit about how 39 minutes, but it just ran for like a minute. So how come it's 39 minutes? Because here it multiplies everything times the number of cores. So these are really the CPU minutes that I have really used. And there are also some of them that I have unused. So different tools. One of the simplest approaches, and this is something that I like to do, is even if I don't know these tools exist, or I'm on a deserted island and I have not access to any of these tools, scroll, scroll, scroll. What I like to do is, it's very simple. I run a series of jobs and I modify it and I look at the timing. For instance, you can start with one core, or you start, as Jon suggested, you start with a full node and then you increase it or decrease it. And here I went in factors of 2 because computer people like factor of 2, but it doesn't have to be a factor of 2. You can do 1, 20, 40, 80. What I did here, and you can try it out in a moment as well, is that for this calculation, I chose 1, 2, 4, 8, 16, 32, 64, 128. And I looked at here with the time, how much do I spend in this step? It's also okay to look at the timing that Slurm tells you for the whole thing. The message is the same. The message that I got from here is that for this example, adding more cores, yes, it makes it finish sooner, 4, 8, 16. But then the benefit starts to be less. So 32 is still better, but the question is, do I want to spend double the compute to get 10 seconds less? But adding more cores gives me penalty. It takes longer. And look at this, 128 cores. It takes even longer. There is no benefit here. Changing from 4 to 128 would be a mistake. And this will be different for every program. And it's not enough to, sometimes people say, well, but the website said that it's really scaling well. I want to verify it. I don't trust the websites because it depends what I do with the program. It depends on the system size. It depends which feature I use. It depends on which machine I run. So again, before I run 200 computations and each of them on 128 cores, I will first take one computation and calibrate it. And once I know, then here I know that this is maybe good, or this. And now I submit my 200 calculations with this setting. And I will be really happy because I will save a lot of CPU. Looking at the questions, thanks for asking them. Let me share the screen. If I want to access more memory, should I ask for more cores if I don't use them? That's a great question. It's one strategy to get more memory. We have seen that one core has a certain amount of memory, 4.8 or 2, or depending on where we are. And one way to get more memory is that we stretch our calculation over many cores, even if we don't use them, but we will use their memory. Very often a better way is to go on high mem nodes. Back to our documentation. Where is the documentation? Here, landing page, Saga, let's say, or any other cluster. Let's look at Saga. What is better is that if I really need a lot more memory, then where are they? Here, big memory nodes. They have a lot more memory, and then they are really designed for this.
No, or already the medium memory nodes.
Oh, here, yeah. And I think on each cluster we have something like this. Not sure.
Yeah, I think so.
So this is step number 1. What can also help is that contact support, because I have also seen cases where somebody wants a lot more memory, and then we realize that we could also go into the code, change the code a little bit, and suddenly the code needs a lot less memory. So sometimes the answer to this problem is to change the code, if we can, if we have access to it.
I mean, and the other, while you build more if you use more memory than one core like fairly gets. But I think our Slurm is set up in a way that if someone would ask for half of the, like for only one core but half of the memory, but someone else would take the other cores and only like the rest of the memory, that it still would work. So I think you're taking away like cores from other people, which could be used, not necessarily can, but if you don't need them, don't ask for them.
Yeah.
Except if you really know what you're doing and you have tried it out and it makes sense.
And question number 10, this testing is also using CPUs, so we have to pay for it. And yes, we do. Is there a way to test your code without actually using up compute nodes? I don't think there is. It's consuming CPU cycles, but I think this is a good investment. So yes, I have now wasted some CPU cycles to find out what is a good setting. But now that I run many calculations that are similar, it will overall save me a lot of quota. It's true that if I don't need to run 200 calculations, if it's only one single calculation, then extensive calibration is can be wasteful as well. But I'm not aware of any way to avoid running on compute nodes.
No, and because often it's like it really depends on the real life conditions, so you can't simulate that easily or you replace it with something else. And I also think like if you run your one calculations often, there's basically nothing what you can do except for trying it out in different conditions and different. If it's like a one-off calculation, and you can maybe guess a bit of how much you need, you can of course try that. But often it's really useful to just like try it as a small test case. If this is possible, if your real calculation takes 5 days, and you can maybe like use a smaller sample which takes 15 minutes, run a few of those, and then use that and scale it up to your big. But sometimes, of course, it's like if the calculation and the fastest one you can like is all the cores of one node or something, it takes like 10 days. I'm not sure. Like
yeah, and I can give another comment, and that's often when we are in a research group, we do often run similar things. And then if I do a very careful, nice calibration, it's nice if I share my findings with my colleagues so that they don't have to go through the same pain again. And we can also help, as NRIS organization, we can help sharing these findings with everybody else. So if you find out something interesting about your program, you can tell us to put this on documentation so that the next person with the same program, the same problem, doesn't have to go through this again. And at least they have a good starting point. So let's document better and let's share what we find as a community. I wanted to.
20 minutes.
We have 20 minutes left. I wanted to introduce the exercise, and let me show you what you can find there and what the goal is. So again, there is a README. Again, there is a spoiler. Similar idea, and what you will find there is the run scripts. You will find, again, a binary. We want to know the optimum number of cores for this particular computation. You will already find a bunch of run scripts. You hopefully don't need to modify them. I tested them this morning. Submit all of them. And let's see what is in the instructions. So copy to your own space. That's important. Please don't run in the please don't run here. Then submit the run script. And then here is a nice command which will extract the timing out of your outputs and sort them numerically. And then based on the timings, you should answer whether it makes sense to run this on 128 cores. And if not, what do you recommend based on these timings of what we should select? And we would return 1145.